you have to consider the different load cases, and you'll end up with basically different actions, all right? Where we end up with then is an envelope of actions on something, and then we have to make sure we design the capacity to withstand that envelope. So it doesn't, for example, it might be fine with the load there, but if the load goes there and it collapses, you haven't designed it properly, all right? How's that going so far? Making sense? All right. The key thing then is when you have a structure, let's do one like that. There's a foundation. All right, and let's say you've got a load pushing it like that. You've got to trace those load paths all the way to the ground. So when you design this bit of beam from here to here to withstand that load, it's no good just designing that bit and going, yes, we're done now. Okay, you've got to say, all right, that load actually goes down here and then down that way into there, and this bit of load goes down that way into there. You end up with something pushing. The earth is going to resist by pushing up there and down there. Okay, imagine that tipping over. Okay, if you don't hold that down enough, that whole thing is going to rotate around there and tip over under that load. So you've got to consider the fact that you've got to design that bit, you've got to design that bit for the downward force, you've got to design the whole thing for stability to make sure your overturning forces, which is that, is less than the righting forces, which is the capacity, okay? Again, it's that, there's the overturning force, from whatever it is, has to be less than the phi times the restoring force, which is Ru naught. All right. In this case, the restoring force is the weight of the structure there, plus the weight of any footings like that, holding it down. Okay. Is that making sense? Okay. There was one, I was coming back to the idiot load. Okay. Let's say you had a structure which was this big, okay, and it happened to be a sign board, and you need to design that to be strong enough. All right. When you design, and that's a solid piece of sign, okay, and there are two legs there. When you look at the loads on that, the wind load on a sign maybe the size of this TV is not actually that big, because it's not very big, right? And other loads on it, the earthquake is pretty insignificant, and you can design your post there. There's no live load on that from people because no one climbs it or is walking on it, so that doesn't really apply. This is where I come to idiot load, where I say, all right, you've got this thing, now consider what else could happen to it in its life. And what else can happen to it is a drunk teenager comes along and pushes on it, okay? And so you have to think, is that plausible? And depending on the situation, it might be yes or it might be no. And what sort of load could a drunk teenager put on this thing, or a group of drunk teenagers? We better make it strong enough for that, okay? There is a principle called proportional or disproportionate actions. So for example, there is a possibility that a car could come and crash into the sign. And so you have to think to yourself, is that plausible? If it's near a car park, yes it is, okay, it is plausible. What if it happened? Would anybody particularly mind if that sign fell over because a car hit it? And often you go, actually no, that would be a fairly plausible thing. Car hit the sign needs replacing, right? It's not going to happen very often, it'll be okay. Or maybe you have to think, no, that sign is that important and needs to resist the car hitting it. Okay? So that's the sort of engineering choice you've got to make about whether you make this strong enough. Where you have an underground car park is a classic example. If you go to an underground car park at Woolies or something, there's lots of concrete columns around, okay? Can you all agree with me that it's very plausible that someone is going to hit one of those columns one day? Okay? They will, all right? You need to make sure that column, if it gets hit, doesn't cause disproportional damage. So, if someone really revs up and hits their car in a major way, it takes the column out completely. It should not cause the building to collapse and everyone die. All right? In fact, if you're designing an underground car park, it's a really good idea to make sure that any particular column could be removed and the thing is going to stay there. Not to say it won't be damaged, like you still have to prop it up, repair it. Maybe it's going to make the floor sag and all the stuff's going to fall off the shelves. And that is a serviceability failure, that's okay, but it's not a safety, it's not going to bring the whole building down. All right. Equally, with a sign like this, you say, yes, an airplane could crash into it. It's not a disproportional damage if the thing falls over because an airplane crashed into it, right? Even though it's remotely plausible. Any more questions on that then?
There'd be a safety point of view that comes
Yes.
into that where you actually want it to fail at some point.
Do you want it to fail? Yes, that's a really good.
Like if you hit it in a
Yep.
car and it doesn't fail, then
You're
more
the
likely
car,
to kill
yes.
yourself. Yeah.
No, that's a really good point. Sometimes we need things to fail at a certain force. That came out from years ago in England. There was a football stadium and a crowd surged forward and people were crushed against the fence. 91 people died. Okay. Fences like that now are designed to collapse with a really strong crowd load on them so that the crowd can actually go past and people don't die, depending what's on the other side. If there's a cliff on the other side, they're going to be solid, right?
Yeah.
But if it's to hold people in an area, those fences like that are designed to collapse so that people will not die against the fence. So yes, there are circumstances where you need things to collapse at certain loads. That adds a level of complexity to your engineering. But yeah, that's not often the case with science and stuff. All right, so the key points, the factor of safety. The factor, if someone asks you what is the factor of safety, it's not easy to give a really straight answer because the factor of safety is both in the way we exaggerate the loads and the way we slightly underestimate the capacity. All right, those two multiply together to make this a factor of safety. The other thing, oh yes, I should have mentioned, when we consider serviceability, we don't exaggerate the loads. And that's because we want to know how much the thing is going to deflect under the actual load, right? In fact, sometimes we normally take, for serviceability, we normally take 1.0 times the dead load, exactly the dead load, plus, and here's another funny Greek letter, live load, a portion of the live load. We don't even often use the full live load because the full live load is a pretty rare thing, okay? Depending what the sort of live load it is, depending what the, what the structure is. And that's all in this book as well. And when you're adding wind into it, sometimes you don't use the full live load in the wind, okay? What's the theory there? The theory is if you're designing this roof for the wind, the live load is actually a guy up here repairing the roof. When the sort of wind comes along that's going to blow the roof down, that guy's going to get off the roof before that, or get blown off the roof before that, okay? Same reason you don't have snow and wind loads together. The wind blows the snow away, okay? So those combinations, they're all in AS 1170. I'm happy to talk about them and help you through that, but that's basically what's going on here. So for serviceability, dead load plus a portion of the live load is the serviceability limit state. And that portion depends on the use, whether it's a building or whether it's a bridge or something. So specifically for this bridge, the one that I'm designing is a bit like that. The bridge has got a nominal load limit of 3 people on it at once. So I'm designing the serviceability for 3 people that it's not going to bounce so excessively that they can't, or deflect so excessively they can't cross it. But actually the strength limitation is a person every meter on that bridge, and it's an 80 meter span bridge. It's actually going to be strong enough to hold 80 people on it. But if 80 people go on it, you can be sure it's going to bend a lot, okay? Way more than it's comfortable, but it should not collapse with them on it. All right, it is 3:40.